Hello and welcome. This is my 8-bit computer in Minecraft. I guess I will start by showing you the inputs here, or the control panel. We have 8 inputs for the address and 8 inputs for the data. And over here we can read or write to memory, and using this we can put in a program. So if I come over here and I do like mcell, which is short for memory select, this will now show me what is in address 0 in the memory. So here it comes, there it is. There is the instruction, and then say I can look at memory slot 2 by hitting that. And so it'll take a minute to get through memory and then pop in, and here it comes, and there's what's in memory slot 2. Alright, and then we can do the same thing with writing, but I don't want to mess up my program, so I will do it on the registers. So here's register select of register 0. You can see it is 0. So let's come over here and we'll write, I'll write a 5. We'll write that, register write enable. So now that should be in register 5. The registers work a lot faster than memory does. So now if I do register select, I should see my 5 again. And there it is. Alright, and I will write that 0 back into register 0. Anyway, so that is the input, and using that, I can put in a little program. Here are the commands, or the instructions that I have implemented. You can read them. We've got, jump, some jump conditions, compare, move, add, subtract, store, load. Right, so the way I implemented this, you can only touch the memory through store and load. So reduced instruction set, architecture, a reduced instruction set computer, RISC. But it's got problems, so we'll get into that later. But it does work. Increment, decrement, and then here's some notes on it. You can read those. You can pause the video or something. So there's my little control panel. These two I didn't get to. This is kill and clock. This are to actually make the computer run. I'll come over here and show you this. This is the output, or at least one of the outputs. It's just a bunch of note blocks, and they're scaled or something, so it is actually address 255. So if I come over here and I put in address 255, I can actually write to the note blocks, and we can get some output. So there we go, and I will hit that note block, and I'll turn memory write enable, and we should get a note coming out. Oh, there it was. Okay. So what I decided to do, or what I have done, is I've written a small program that basically just takes from memory, and it takes some notes from memory and then puts them onto the note blocks. So the idea being that it could like play a little song or something that's stored in memory. Now I haven't actually run the computer while I've had it recording, so I don't know if impact wise this is going to be good. Let me just check that everything is set right. Register 0 should be at 0. That's the start of the program. Register 0 is the program counter. Register 2 is what keeps track of where in the notes we are. It should start at 8. Is correct. And the memory is still good, so I think that's everything I need. So I'll just turn on the clock. So now the finite state machine will start running, but it's still, kill is still on, so it's not going to do anything. So once I hit kill, it should start computing. And now we can sit here and we can watch these data ones, and they will reflect what's on the data bus. Now the thing is, the clock for this computer is I had to make it really, really slow. So it actually takes it quite a long time to do anything. It's several million times slower than the processor it's based off of. So it's actually a lot more interesting to think about what it's doing, you know, to imagine what's going on, than it is to actually watch it process. There we go. There's the address. So I'll come over here because it should shortly. It will actually send the data to that address, and I believe it'll set off. It should set off 2 blocks or 2 pairs of blocks. I don't remember which ones, but we'll wait. Oh, there goes one. And oh, I must have accidentally put a 0 in, so it wouldn't set off the second note block. 0 is empty, as in don't play anything. And now I'll come over here and I'll show you the actual computer. Or at least the circuits of the computer. So there it is, over there. I will start by showing you the RAM. This is the RAM, over here. I did not lay out every block. That would be ludicrous. Got these nifty mods on here that let me mess with stuff. Yeah, I can just say from that creative mode kind of ruins it. From that block to that block, set 155. Yep, num block. Oh, whoops. There we go. And I can just set it to a material, and then I can like copy it and paste it and stuff. So it really helps do that. Anyway. So here is the memory, the random access memory, the RAM. It has 255 bytes. That is practically nothing. That is like less than a text file. But it accomplishes my purposes. I believe, if I remember correctly, there are 8 rows, and each one of these rows has 32 bytes on it. I'll show you how long that is. Flying, flying, flying. Back here. Somewhere is the end. Somewhere way out there. I can't see over there anymore. I have the render distance on normal, I think. Because when this thing runs, it kills the performance of my computer. Okay, so here's the end. And I will show you how memory works. So each one of these, from here to here, is where the memory is actually stored. So there's 8 levels, 8 copies of the same thing. So here you can see I've actually got data here in that one. This is one of the notes. Okay, so here is the memory. Now, as you can see, there's a difference between that one and that one, namely that these repeaters are off here, and these ones are on here. So what these do is they will block this repeater from changing. So if this is on or this is on, that comparator won't let them through. And if that is on or that is on, that one won't change. So these two are both the address, making sure you are on the right memory. So right now the address bus, these 8 lines right here, these double wide lines is the data bus, are the data bus, whatever. This is the address bus. Right now it has nothing on any of the lines, so it is 0. So slot 0, or memory space 0, whatever I want to call it, is activated right now. So it's enabled. So if I then say I turn this one off, this is the memory select, so that comparator will then let it through and put it onto the data bus. Whatever's on there. If there's nothing on here, it will put nothing on there. If there is something on here, it will put something on there. And then the write enabled is right here. If I blow that up, it'll let nothing into there, and it'll be nothing. But I don't want to mess up my program, so I'm not going to do that. So the way this addressing actually works is we've got the address bus comes in, it turns into here, and then it just continues on here. So if there is a 1, okay, so all 8 of these lines, each spot here is either a torch or just continuing like that, and all 8 on this first one are just continuing. So if any one of these lines has a current or a 1, it'll come in here, and it'll come in here, and I just repeat myself, it'll hit that and continue down all the way down to the bottom, where it will then come in here and lock it, and then come up here and come all the way back up and lock all the ones along the way up. Yeah, so address 0, they're all zeros. Address 1, you see we've got a torch here. See? And so this torch powers it and comes in here, and this torch is what's locking that. If I blow up this torch, it will no longer be locked. Or, better yet, if I use the address bus, then we'll come in here and see this continues the signal, and now 0 is locked, but it kills the signal here, and 1 is unlocked. But if I come up here and put something on address 2, then 1 will be locked, but 3 over here will now be unlocked, because it's 1 plus 2. It's binary. That's how binary works. Where's that torch? There it is. Gotta make sure to put this back, or I will have broken my computer. There we go. So now 1 should be unlocked, and 1 is locked. See? Okay. And that is how the address, or the RAM works. So over here, this is my finite state machine, my FSM, that controls all the circuits and enables them and disables them as is needed to run the computer. So the way this works is we got 3 of these thingies. I do not know what they're called. I think maybe, yeah, I'm not even gonna guess. But I know this one is called the master and this one is called the slave. And in order for a signal to come all the way through, the way I've wired it is that the clock, which is right here, which is very long, I will show you how long. On and off, and it's going to turn on in a minute again. That's how slow the clock is. But anyway, these are wired in such a way that it can only transfer the signal from here all the way through once the clock has gone off and then on and then off again. It has to make a full transition in order for this to put the signal all the way through. Anyway, so there's 3 of these, and so I can use these as like a little binary counter to count what state I'm in. So these, I didn't even, so these 3 can be on, 1, or 0. And now what they do is they come in here, and you can see there's more stuff coming in here. There's 8 on top and 8 on bottom, and this one has nothing. And what these are the inputs into the finite state machine. Each input comes in and it has a line saying whether it's on and another line saying if it's off. And then what I do is I just run along here and I stick torches on. So this torch, in order for it to be off, this has to be on. And that torch, in order for it to be off, this has to be on. So using this, I can create conditions saying, like this input has to be off and this one on and this one off in order for this line here to be off. And what this does is on here I can throw some torches on there, and now those serve as outputs. So only if these conditions are satisfied will this turn off, and these torches will turn on, which then shoots the output on or off as I've programmed it by laying of torches. Now that the kill switch is off, I'll show you what these are. So this is the first one, this is the second one, this is the third one. This signal is the kill switch that I just turned off. And then these 8 over here are what is on the input register, which just takes whatever command you're currently on and sticks it in there while it's executing it so it can remember what it's doing. This is the most significant bit up here, then it goes down, 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 and then it comes back over here, down, 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 and then this is the least significant bit. So on those giant RAM structures over there, this is like the one that's on the ground level. And then this one over here is like what's on the top. Like they are over here coming out of the input register. So every command will start out in the state of fetch, which is where it increments the program counter and puts it onto the memory address bus. And then it goes to decode, which is where it takes it from memory and sticks it onto the input register. And so the values you were seeing there was just what's on the input register. It doesn't matter, won't use it. And then I've got states for all the different commands and how many clocks they have. So if we look, here's part of the problem with this machine here, is store has fetch, decode, store 2, store 3, store 4, store 5. So there are 6 clocks to execute store once, and I believe store is used twice in a single loop to play a single note. And then load is the same. It takes 6 clocks to do a load, and it's just really slow. But then there's some commands like decrement and increment and move and jump, which only take 1 clock. So yeah, those ones are much quicker. But yeah, I can actually show you. So, the conditions are satisfied that it is convinced it is fetch. So this one is off. So all the torches here that are associated with fetch are on, which come over here and turn on the right circuits. So register in of 0, register write enabled, memory address register write enabled, we got adder mux 1, and ADR, I can't remember what that stands for, like address, or yeah, I can't remember, I just copied that from a schematic, but I recognize what it's referring to. It's over in that corner over there past the input register. But yeah, so fetch is all ready, the circuit is doing what it's supposed to, but it will not progress until the clock goes. So I will just come over here and push a button, do a little manual clock, click, clock, and now it is jumped to the second part, decode. So now it's incremented the program counter and it's put it on the address bus. So the address bus should say 0 right now. Yep, so 0 all the way up. And now it is taking from memory 0. I'll come over here and show you. Just taking whatever is in memory address 0 and putting it onto the data bus. So we got on the data bus, on there. Off, 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 on. It's just taking what's ever in memory address 0 and putting it onto the data bus. And then that is coming all the way over there. You know what? I'm going to get my little jumper tool out. Part of the mod allows me to teleport with the compass. It's kind of nice. So if we come over here, here is the input register, and it's connected to the data bus here. And if you're wondering, all of this is to let a signal go both ways. because like that's an output onto it, and this is an input, and so I need the signal to go both ways on the data bus. That's why there's that. So here's the input register. Whoa, my mouse just freaked out. Here's the input register, and here is the input register write enable. It is off. Well, not really. It's on, and then it turns it off, which unlocks it, which lets it write. So input instruction register, yeah. So it writes, yeah. So then that comes out, and that is put over this way onto the finite state machine. So now we have all these 8 ones reflecting the current instruction. So from that, it can then tell that, oh, I'll come over here and show you this too. So it's on clock 1 now instead of clock 0. So with all that, oh, actually it's still on decode. Right. So I will clock it again. Clock. And now it is on clock 2. So with clock 2 and the instruction register properly filled, it now knows that that the instruction it is executing is store. So it's on store, and I can sit there and keep clocking it, and it'll go through here and activate the right circuits that are needed to do that instruction. Here we have, this is part of my ALU, arithmetic logic unit. This is a small multiplexer, and this is just an adder. And so we've got 2 small registers here. This is the source, and this is the destination. That is not right. Yeah, it glitches a bit when you move it around with the commands. The Redstone anyway, when you're using the world edit commands, like I was using with the diamond axe over there. Anyway, so this ALU, it can't really do much. It can add, subtract, increment, decrement, and move. And that's it. I didn't implement everything. I just made a really simple computer. And as you can see, I didn't actually do the full circuit anyway. This is actually supposed to jump over to the data bus, so then you can pull in from the data bus and use that as a source, but I limited it so that you can only access memory through the store and load commands, which made it a lot simpler on my part, but also probably slowed it down a bit. But also, because I'm only using 8 bits instead of the 16 bits that this processor was designed for, I can't do as many instructions. So it's kind of limited in that aspect anyway. This is an adder and a multiplexer, and that may sound familiar because it's basically the same exact thing that is. This is in the actual MSP 430, the processor this is based on. That's a lot more complicated. It does a lot of things. All this does is add. So it can add constants, a constant of 0, constant of 1, and I've got the whatever's on the data bus, and I've also got part of the instructions. So the jump instruction uses the first 3 being 0 to do just a regular jump, 0, 0, 0. And then you put in a 2's complement number of how much of an offset you want. So if the first one is 1, then it's a negative. If the first one is 0, then it's a positive. So this just continues up whatever it was. So with 2's complement, you can directly add positive and negative numbers, and they will come out to the correct thing, assuming it doesn't overflow. And so that's what that does. That's when I use this option of the multiplexer. I guess I could show you how the multiplexer works really quick. So there's 2 inputs here to the multiplexer. 1, 2, and right now this one's on. And so what that does is they come over here, and then there's these torches here. So you put it in a signal here, So if this is on, and I want the output of the multiplexer to be on, if I want this output to come out, or that input to come and be the output, then I need this torch to be off and that torch to be off. Otherwise they're messing with it, and you're not getting your actual output. But if they're both off, then this will, do the opposite twice, which is the same thing. So it'll continue it forward. So what it is these are just binarily, selected. This one just continues the signal. This one makes the opposite of the signal. This one's the same, but the other way around. And this is which one's being selected right now. So you see this is 1 and this is 0. So this one, which is 1 and 0, is off. So it's what's putting the output. And then this one is just 0, 0. So if I actually break this, now this one would be able to put its signal out. So like if this was on, then this would be off, and then this torch would be on, so it puts its output. But this is 0, so I want it to stay 0. All that's left is here. These are the registers. They are almost the exact same thing as the memory. They've just been slightly modified, but it's the same concept. Yeah, here's the registers. So this is register 0. This is the PC. I can come in here and I can reset it. So look, it's got a value of 1 right now. And I can come over here and just, now it's got a value of 0. Alright, so I'll show you, I'll step through the fetch command with you. Or, I guess fetch is only part of a command, part of an instruction. So it's on fetch, so turns on some specific circuits. So let's see, the one I'm looking for. Oh. So it doesn't have anything going in to say what output from the registers it wants, which means it's at 0, which means whatever is in register 0 is being output. So here is the output. You can see it's not locked. If I come over here to register 1, it is locked. Register 0 is a value of 0. So there is 0 being written onto here. It then puts it into the adder over here and increments it. So what the fetch command does, I've said it before, but it takes what's in the program counter, puts it into the memory address register. Oh, I didn't show you that. This is a memory address register. It's the same thing as those other registers. It's got a little multiplexer here that I don't use. But yeah, same thing. If you want it to write, you have to unlock it, which it is doing right now, because fetch writes to it. But if I do that, then it's locked. So the memory address register is being written to, and what is being written to it is what is being read out of register 0. So if I follow this line here, comes over here, up, and it turns this way, and it turns into this little tiny multiplexer that I don't actually use, and then it comes over here and it goes in. So register 0 is coming in, and the memory address register write enable is 1, so it's putting it through. So that's the first part, and then the second part of the fetch command is that it takes this and then it increments it. So I follow the signal here, it comes this way, it comes over here, and it turns over this way, and then it comes over here, and it turns into the adder. So R0, register 0, PC, is one of the inputs for the adder. Now with the fetch command it also turns on this, which is adder mux 1. Yes, this is the adder mux 1 line, which is turned on. And so what this does is it selects our constant value of 1. See how it's 1? It takes this constant value of 1 through the multiplexer and uses that as an input for this adder. So then the output from the adder comes out this way, and it comes out this way, and it comes all the way over here. And this is the ADR, which I can't remember what it stands for. It's basically like the registers, except it just stops the output. It doesn't remember what it was, it just stops it or lets it through. So ADR is on, which means it's letting it through. So this signal, which is the incremented PC signal, comes through, and it's coming down the data bus. It touches everything. It's not being written here because this is, turned off. But anyway, you really can't fly down this very well. So I'll follow it. It's coming along this way. That's an output from the ALU. It continues this way, and it keeps going this way, and here we go. Now is an input. This is an input to the registers. RN 0 is set. So what that does is, in theory, it should work the same way as the R out, but it wasn't. It was having some issues with the clock and the timing, and it was actually overriding itself in certain commands. So what I did is on the RN, it's actually register 4 instead of 0. And so then this is just the RN. If this is enabled, then it's 0. So that's just a little hack I did to make it work. But anyway, so that's just the same addressing technique I've been using in other places. So this input signal comes in, and if we come over here to register 0, you can see the signal comes down here, and it comes in here, and then right here it is not locked, so it lets it through. Except it only gets through part of it. This is another, this is the modification here. This is what separates it from RAM, is that this will not write until writing is disabled again. Then this will flop, and then this will have written through there. So if that makes any sense at all. Yeah, okay, I'll just do this. See? Alright, so there, it flopped. So now that one's locked and that one's open, so it wrote. Now the next time you say to write, this is what the idea is. So when you tell it to write, it won't write until that command is done, so it'll continue its same output. So where this is, or where this was 0, it will be stable as 0. It'll continue sending 0 out until the next clock. Then it will write, so we have a stable circuit, and it's not just going up and up and up. Because you see, right now it's incrementing it. So if I do let this through, this will become 1. It will increment it, and then the signal will switch, and it will want to write 2. So I'll do that for you real quick. There. Now it's 1, and now this is going to catch up. There it goes. The adder just added 1 to 1 and got 2. So now it wants to write in 2. And that is how the fetch command works. And then the other commands are, the very similar concept. They do different things though. Yeah, that's how it works.